Okay, so today we will do things a little differently. Instead of 45 minutes on the problem, we will spend 35 minutes and leave 10 minutes for any questions that the interview might have and discussion. So far, we've done Twitter, so today we'll be doing chess. The first thing we would do is ask some clarifying questions. We start with, do we support multiplayer? I'm assuming we do, because if we don't support multiplayer, it becomes the user versus the computer algorithm, at which point it becomes more about the user interface and the design of the user interface, and less about the system uh, behind it. So the next question would be, do we do multiplayer over the local network or over the internet? If it's over the local network, it becomes easier because you could have one of the players' systems be the host and the other one being a client. But if it becomes over the internet, you would involve parts like a central server that keeps track of games and connects different users. So if it's over the internet, you would be serving more than just two players. So you could have a platform which uh, supports multiple games and multiple players, something like chess.com or Lichess. So that's our third question is, are we doing a platform like Lichess? The next question is the number of daily active users we're expected to serve on the platform. Lastly, we figure out the number of games that will be played during peak hours and in total in a day. Now we'll talk about everything involved in the system. First thing that comes to mind is the daily active users. We'd have the user management, the user authentication, the game management, which is matching one game user to another for a particular game. Now we go into the data that each of these holds in the database. So for user management, we would have usernames and hash passwords along with some user data. The user data, which involves mostly game history for each user. For user auth, we have usernames and auth tokens. For game data, we would consider the moves made in a particular game, the game ID, and the outcome of the game. Assuming we have 10 million daily active users and they play 3 games a day on average, we would have 15 million games a day, not 30, because we would have two players playing each game. So 15 million games a day is roughly 450 million games a month, and that's 5.4 billion games a year. Now, in majority of the cases, once a game is played, the user is unlikely to revisit the game. So we can store this in long-term storage that's on the disk. In our case, we'll also be saving them in the database. Now moving on to the short-term storage, that's games that are ongoing can be stored in cache without hitting the database for every move that's made for every game. In this case, we're going to assume that the read-write should be about 3:1 because you have a player playing a move with the opponent reading that move and making their move. Let's add in a possibility of a user reviewing their own game, so makes it 3:1. Talking about the memory that each of these is going to take up. For user data, we'd have usernames, which is about 20 characters long, hash passwords, which set aside 256 bytes for that, and the user data, which is mostly games. In chess, you would have 64 squares, with each square labeled from A1 to H8. So for a particular move, you can write a move in 7 characters. So let's say for each side you'd have 7 characters. In total, that's 14 characters. Assuming 100 moves per game, you would have 1400 characters. That's 1.4 KB. Moving on to the user auth data. For this, we would need username and auth token. But instead of usernames, we could replace that with a user ID. Since username uses up 20 bytes, we can just replace that with a user ID, which would use up maybe 3 to 4 bytes. Using that would optimize storage. So we save the user ID along with the username and the user table, and we use that same user ID for user auth. Along with that, we use auth tokens, which is about 128 bytes. And for game data, we know that the moves will take up 1.4 KB. Game ID roughly about 4 bytes and an outcome of 1 byte. We can round that down to 1.4 KB. Now moving on to the next question, which is to use SQL or no SQL. So in this case, I believe that since we're saving all of our data in cache and only moving it to the database once we have completed the game, I think SQL does the job. Now moving on to the diagram, we start with drawing all of the blocks first. First thing would be the user interface, then we have the load balancer. So then we move on to the user management service, and that has its own cache. That's the username cache, which stores the usernames. And we have the user DB. Same goes for the auth service, the auth cache and the auth DB. And finally we'll have a game service, a game cache, and a game DB. And we're going to connect them. This is how a sign up request would go through. So it would go from the user to the load balancer to the user management service, which checks the username cache for an existing username. If it exists, it returns that directly to the users, asking them to pick. Now, if the user cache doesn't have that username, it checks in the user DB. If the user DB has it, it saves that in the cache and returns that the username is not available for use. When a user profile is updated or created, the user management service directly sends that data to the user DB, and it can fetch that data from it can fetch user details directly from the user DB. Moving on to the auth service, let's assume a login request comes in from the user. It goes through the load balancer to the auth service. A login request or an auth token validation request would go through to the auth service. And in case of an auth token validation, it looks up the auth cache to see if the auth token exists in the auth cache. If it exists in the auth cache, it's returned directly. If it doesn't exist in the auth cache, the auth cache looks up the auth DB and it fetches the auth token from the auth DB and saves it in the auth cache for subsequent requests and returns that to the auth service. Now, when a login request comes through to an auth service, we need the user credentials that's stored in the user DB. So we use a read-only fetch from the user DB to get the username and the hashed password from the user DB. And the auth service validates the user and updates the auth token for a particular username in the auth DB. Now, when a game request comes through, so the game service looks up the game cache for an existing game, and if it exists, then it will return that game to the game service. If it's not found, it returns not found. And once a game is completed, that game is written to the game DB, and all games are fetched from the game DB and returned to the user that way. That's the completed diagram. At this point, I used 40 minutes of my time. I used the last 5 minutes to explain my approach. I used a total of 47 minutes for this problem. This condensed version is about 10 minutes, and the longer version should be somewhere here.